when we do a matching, we have to work with the Smith chart in order to see the true reason of why we don't have a matching when we don't have a matching. And if we work with the 2D graph, we won't be able to determine if the return loss has insufficient results, because it is here and it is a little bit capacitive and inductive or resistive, or here or here or here. We will get the same return loss from all these points, and we have to determine how to fix this. We can of course do a try and error process, but this is not efficient at all, and we don't have to do that, as you remember from our previous sessions. So now I have selected a bandpass filter which is relatively matched, but it can be better. I took it from our old memories from our lab, and this is an old bandpass filter, and we will see how it is performed now and what we will get at the end when we go through the process that we have studied. And we start again by calibrating the network to the frequencies of this bandpass filter. Okay, so I have set the network analyzer to 1 to 3 gigahertz band. This bandpass filter that I'm holding is was designed to work between 2.15 to 2.35 gigahertz, and I have presented a wideband in order to see it stop band and the pass band as well. And it will give us a fine view of the stop band and pass band on the Smith chart. And I start by connecting the bandpass filter to the network analyzer ports, and we can actually see now the reflection response of the filter. As you can see, this is not in the center of the Smith chart. You can see that, although it's not so far away. And if we look at a 2D graph, then we can see that the level of the return loss is quite well. It's between 10.7 to 15.6 dB, but when I look at the Smith chart, I can see immediately that I am able to get much more than that, because the response here, it's not centered. Since it's not centered, as you've seen before, the marker 2 is the one with the minus 10 dB, 0.7. As you can see, it is more far away from the center than marker number 1. Assume I could take all the filter response in its pass band and move it to the center of the Smith chart, then I would get a much better response from the filter, and the return loss of the filter would be much better than what it is now, even though for many applications this response might be sufficient. But I want to do better than that. So I want to move this picture to the center of the Smith chart in order to get a better response, but I'm now in a problem. What is the problem? As you can see here, if you look at the filter, okay, then we have calibrated the network analyzer up to here, up to this reference plane, but the filter starts here. When I put my finger now. The problem of this device might be the connection between the connector and the PCB, but in order to fix that, I assume that we have a good enough 50 ohm between here and the start of the filter, the beginning the input edge of the filter, and I want to see the picture here of the Smith chart, because I don't know what the picture here is. I only know what the picture here in this reference plane. So I don't know if this response is resistive as it is in here or not, because I don't know what it is. I can assume by calculating the length between the reference plane of the calibration and the reference plane on which I want to see the response. But first I want to fix this Smith chart view to reflect the return loss at this reference plane and not at this reference plane. How do I do that? So first thing I want to do is to fix the reference plane so it will reflect the return loss of the filter at the right reference plane. So here's the trick. I took this wire, I deliberately choose the right wire so it will come out nice in the video, and see how I've soldered it in the input terminal of the filter. See here. And we know that when we have a short circuit, we're supposed to see it on the left side of the Smith chart, and when we look now at the Smith chart, if we will move the camera to our Smith chart, you see that the markers that we used before are not located on the short circuit location. They are located here. Why? Because we have actually a short transmission line between here, and in high frequencies, and although 2.2 gigahertz is not so high, but this distance is not neglected in this frequency, and that's why the Smith chart view has rotated, as we have seen in we have studied in our sessions. And first thing I want to do is to put the Smith chart view here, so the short circuit that we have now on the filter will be placed here. When it is placed here, then we actually get the short circuit view at the right spot. And I do that by using the electrical delay feature of the network analyzer. I will show you now how it is done. Well, the feature that we have to use of the network analyzer is the electrical delay. As you can see here, it is in the scale button, lead us to the electrical delay. The electrical delay is a virtual transmission line, and by changing the delay time, I am actually able to rotate. As you can see here, I am actually able to rotate. You see how I'm keep rotating the image of the Smith chart. Now I have rotated it to the right, but actually I don't want to rotate it to the right, because the right movement, clockwise movement, is a movement that comes from from a longer and longer transmission line. The fact is that I want to move it to the other side. Okay, so I will now move it to the other side of the Smith chart, left side. As you can see, it moves towards the short circuit point, and it also gets shrinked. Why it is shrinked? Because the short circuit is a short circuit for all frequencies. So if this is the case, so all frequencies should be at the same point of short circuit. There's no transmission line issues here. So as you can see, when I'm approaching the short circuit point, as you can see here, okay, then we have almost a point at all frequencies. We have compensated now all the distance between the reference plane of the calibration and the reference plane of the input terminal of the filter. Now it is not located correct, and we have compensated the transmission line, and now when we look at the Smith chart, we will see the actual true view of the filter, this bandpass filter response. The next thing I have to do is to remove the short circuit and go back working with the bandpass filter again. I have removed the wire, the short circuit wire, and as you can see, the picture of the Smith chart have changed comparing to the previous time that we looked at. Previously it was here. Okay, so it was here, some kind of, it was as it is matched to something around 40 ohm. But when we have compensated the reference plane as we should do for every time we go through this process, as you can see, we understand now that we don't have to make a coder wavelength match in order to change resistive to resistive. The only thing that we are here is that we have to add serial inductance. As you can see, if we will add a serial inductance, all this picture will go up along the unity circle line, and we will get a better matching from this filter. And you see here that the first component of this filter is a capacitor. So the capacitor might be very too low because it is a serial and it has a too strong impact. But I will refer this filter as a black box, and I will not touch the filter itself. I will add components in order to compensate this matching by adding the serial inductor in this case in order to compensate this matching. Okay, so as you can see here, I cut the input transmission line at the input terminal of the filter, the reference plane when we wanted to add a serial inductor. And I will take 1 minute to make a note here, because as you remember, I have emphasized that it is best to be prepared in advance by designing a pi network that can accept a serial and parallel matching components. In this model, no one has prepared this pi, so I had to cut the input transmission line in order to add the serial inductor. This is a very old, I don't even know who designed this bandpass filter, but it is a nice bandpass filter without a pi network for matching. So we are doing it actually the wrong way by cutting the line in the input of the filter. So I added the inductor. As I told you, the best is to take S parameters from the network analyzer, to put it on a simulator, and then to figure out which is the right components to use in order to do the matching, and then to go to the lab only once in order to implement what you have seen in your simulator. I have seen that within the area that I have here, and within the accuracy that I have in the cutting, in my cutting capabilities of the transmission line, I have seen that if I will place a serial inductor of 2.2 nanohenry here, then I will improve significantly the return loss of this filter. And as you can see, if you remember, the return loss previously was here, and now we have moved it to the center. Previously we had worst case return loss of 10 dB, Now we have a worst case return loss of 15.6 dB. If we will look at the log magnitude format, then you can see here the worst case point, and you see that in general we can say that the return loss, the in-band return loss of this filter has been improved. Okay, we can add the other port return loss now, and if we add a new channel, this is on display, number of traces, we will add another trace, and we see that port 2 need to be matched as well. It is not matched so well, and if we will look at the Smith chart for both port 1 and port 2, as you can see here, I will take the log phase option. You can see that the area of interest in this filter is placed here, so we have to lift it up a little bit with a serial inductor and then use a parallel capacitor to pull it a little bit down. Of course, we will not do that because this is the same process, but when we will do the same thing here, then we will be able to move the return loss to the center of the Smith chart, as we did in the port number 1, the yellow one. As you can see here, we have improved it significantly. That's it for this session. You saw how we took a non-matched device, or non-matched enough device. We looked at the port of interest, and we succeeded improving it from minus 10 dB return loss to almost minus 16, and in this case we can even do a little bit better than that if we had our a pre-designed Pi network here to work with. It would have been easier. And port number 2, we won't do that in this session. You can understand now how we work, and this is it for now. Thank you for watching.